Hello, Jeff Disher here again. Today I'm going to talk about something that's kind of Linux specific and kind of technical, but still kind of interesting, and it points out some interesting differences between 32-bit and 64-bit assumptions. So this is all about the X32 ABI and 64-bit processes. So what does this mean? Well, first of all, we're going to go through talking about what was the need for 64-bit processors. Why did we think this was so important, and what were the legitimate and illegitimate reasons for this? Then again, what are some of the costs that we had to absorb when we went through this transformation? We upped to 64-bit, but this did cost us something. What were those? What were some interesting advantages that 64-bit had on x86 hardware specifically? This refers to, by x86 here, I mean Intel and AMD processors. So then we're going to talk about kind of an interesting innovation based on some of these observations called the Linux X32 ABI. And some future relevance considerations regarding a lot of this work and kind of how some people are looking at it and kind of my own opinions of how I think they should be looking at it. So first of all, what was the need for 64-bit? Well, it all came down to a limitation of what we called the 32-bit address space. Now this meant that by address space here I'm talking about the size of memory. It's what's called the addressable space. So what can you address within a 32-bit piece of data, right? Every piece of memory has an address. They all need a number. So we've got 32 bits of data with which to express that number. What's our limitation? Well, it's 4 gigabytes, which is just over 4 billion addresses. And remember, this is a per process limitation. Some people have said that this meant that you couldn't put more than 4 gigabytes of RAM inside a computer because, oh well, without a 64-bit processor, I won't be able to use them. That's not actually true. Most architectures have ways of handling this case such that even if you were only on a 32-bit processor, you could still have a system that had 8 or 16 gigs of RAM and you'd just be fine. It just meant that each individual program you were running could not use more than 4. So there's some other potential benefits that come into other areas of this. One which is kind of potential, but often not really where you see the benefit, but still kind of an interesting possibility, and when it does play up, is memory copying. Now this just means that when you're actually trying to move pieces of information from one area in memory to another through the CPU, if you have a 32-bit registers to store the data in, sometimes it's going to be faster. Now usually you take a different approach, so it doesn't benefit from this, but in some cases this can actually matter. And the other area where this was very seriously needed is when you're doing math on very large numbers. Now, of course, by large numbers, I mean here billions and billions. So that's an area where this does sometimes come into play, and in those situations, this was a huge benefit. So what were some of the costs, though, that came into play when we did this change? Right, nothing's for free. So one kind of core problem behind this is that most of the actual information that you store in memory, that a program's storing in memory, is just what's called a pointer to another piece of memory. It is that address of another piece of memory that it's storing. So that's what most processes are actually storing. And so if you had a 32-bit processor, that's going to be 4 bytes of data that you're actually using to point to something else. Now when you go to 64-bit, now it's 8 bytes. So suddenly some aspects of your data storage actually doubled in size. So this does make things bigger. And of course, everyone thinks, well, okay, bigger numbers wasting memory. Well, what's the difference? Memory is cheap, I'll just buy more. It's like, well, there's problems with that. Memory takes power, first of all, to run it. Wasting it to do nothing seems kind of pointless. And also, bigger numbers also waste your cache. Now, the cache is a small piece of fast memory that sits between your CPU and main memory. The reason why it exists is that the CPU is way, way faster than main memory. So the cache is sort of intermediate. It's fast memory to try and hide the cost of interacting with memory. But now you're using twice as much space there too, so you're getting much less benefit out of the cache. So you're actually going to see lower performance. Often this is what we refer to as cache density. It's a term you might hear people throw around sometimes when they're talking about this, which basically refers to how much useful information am I actually storing inside a fixed size cache. So if your numbers get bigger to store the same kind of information, well, now you've got lower density. So you're going to see a performance loss. And the other thing to remember is relatively few tasks need this. there aren't very, just the reality of it is there aren't very many programs that need more than 4 gigs of RAM or need to work doing math in billions and billions of numbers. Most things just don't work that way. So the benefit for them is going to be effectively non-existent, but the cost for them is real because of all these reasons. Now, an interesting thing to point out, though, is that there are some special advantages that the x86 processor has when it moved to 64-bit. And this has more to do with problems with their legacy of the x86, because remember, it's a very old processor. Most of the parts of it we interact with today were largely designed and implemented in the 80s. So the reality of how to build CPUs has changed. And there were some limitations they had because of that legacy, which were really slowing them down. Specifically, this is few registers. Now, I've referred to register a few times. I've talked about it in some other talks. Basically, this is sort of the small piece of memory that sits right on the chip. That actually, it's what you use for sort of your working storage. And so, if you have not very many of those, you can't do very many things at a time. Every time you need more memory, more information, you have to now go to memory again and again. So it really slows you down. And what they did with the x86 is when they added 64-bit support, they also added a lot more registers. So suddenly you could do multiple things at a time. That was no longer a problem. But of course, well, all the data was bigger, so everything was slower. You were taking longer to access memory, things like that. So the real benefit here was you had less of what's called a memory spill. Now this is what it's referred to when you're trying to work with a bunch of pieces of data, but you don't have enough registers to hold them all. So you'll do what's called spilling memory you're not currently using but are going to use soon into a piece of memory. Now, as the difference in speed between the CPU and memory has increased, as the number of processors and cores that are interested in what's going on with memory have increased, the cost of doing this has correspondingly increased as well. So this is it's kind of a downside to the x86 legacy, where they were really being punished by this because they were running out of registers, a phenomenon a lot of people refer to as register starvation. So what's the Linux X32 ABI, and why am I talking about this? Oh, and first of all, just a note of clarity, ABI refers to Application Binary Interface. It's sort of the common dialect that connects your program, the compiler that you're using to work with it, and your operating system. Just kind of the lowest level way of describing what does it mean to be running a program on this computer. So what this tried to do is it tried to be the best of both worlds. It said, all right, let's just store 32-bit values inside the new registers. So now we've got all these new registers, but we're not going to increase the size of memory. And there's certain limitations to how they could do this, but for the most part it actually does work. What this means is you get effectively no memory growth because you're not using bigger numbers anymore. Everything stayed the same size, which means you get to maintain your pre-existing high cache density. You're not diluting your cache with useless zeros anymore like you would in 64-bit. And you get the benefit of all these new registers that were added with the 64-bit processor. So now you end up with something that's much, much faster. And the great thing is, relatively few programs actually needed to change. There were a few important ones that did, and this is part of what held back adoption early on. But for the most part, you just recompile, right? You just take your program, run it through your compiler again, just say, oh, I use X32, and now it works. And you get this benefit for free. There's no more memory increase. You're not changing the requirements for your user other than saying you have to be running on a relatively recent 64-bit processor. And that was fine. So some people, though, have questioned the future relevance of this. They've said everything should be 64-bit going forward. So 32-bit and X32 are irrelevant. X32 was too little too late. I actually think this is very, very wrong. And this, of course, is getting more into my personal opinions regarding this. But there's a few parts of reality that have not changed just because they've been so single-mindedly gung-ho about 64-bit adoption. One is, few tasks need more than 4 gigs of RAM. That's just the reality. If you're trying to say, how many files do I have in this directory? Well, that number's been about the same for a very long time, because that's not a technical thing, that's a human thing. Remember, humans have been around for tens of thousands of years, and we haven't really changed much in that time. It just turns out that we tend to simplify things in our environments. So our computers being able to track billions and billions of things at once doesn't mean we can or want to. So a lot of things have actually just stayed the same. So there's no benefit to them. And also, large number math is rare too. Relatively few programs are actually worried about doing a lot of computational heavy work using really, really large numbers. It just turns out that it doesn't come up that often. And also, most software is very old. If you look at a lot of the tools that kind of underlie sort of the base parts of the internet, or a lot of the web servers and kind of mid-range servers like that, a lot of the software has been relatively unchanged since, I don't know, about 30 years ago or so. So why do they suddenly need to have this like huge ways of looking at memory? Remember, they were implemented in an era where that's not how you looked at things. You need very, very little. So why would you change them? All it's going to do is make them slower and make them use up more resources. So my claim is X32 should replace 32-bit. Because wherever possible, it means that, okay, now you're going to be faster because you have the new registers, but you're not getting the extra cost of going to 64-bit. So this is partly because the way I look at it, the foreseeable future benefit over 64-bit is quite realistic. It's not to be ignored. Most of these issues I pointed out are not temporary. Remember, a lot of problems just aren't that big. So treating them all like that big doesn't really help you. This is like telling the kid running the lemonade stand that, oh, you need to go industrial and get all these machines and everything to do this, because that would let you do more. It's a kid running a lemonade stand. All you're doing is making his life more complicated. You're not going to increase his enjoyment or sales rate by doing this. Sometimes the limitation is not technical, it's environmental. It's just, this is all I need to do. So why solve it in a more complicated way? So anyway, I hope that was interesting. If you're interested on kind of that lower level technical level, yeah, take a look at some of the work that's been done with Linux X32. It's a really neat idea, and their benchmarks have been showing that it has quite a benefit. So it is something worth taking a look at and worth adopting more wholeheartedly. And going forward, if you want, just send me an email here or leave a comment if you've kind of a question or a rebuttal or some other comment regarding this video, or if you have suggestions for any others. And as with all my other videos, remember that you can always trust me at this URL or QR code on Open Autonomy. So anyway, let me know what you think, and I'll talk to you later. Bye.